All right, so here we're going to do a little introduction to parameterizations before we actually get into the notes on it. I just kind of wanted to give you a brief little explanation of it. So essentially what this is, what we're going to do is basically write functions, usually functions that we already know, but we're going to write them in such a way that we can kind of break apart the x and the y and see what they're doing individually. And so to illustrate this, we're going to start with a extremely simple example. This is our x-axis, this is our y-axis, and we're going to start by looking at the function y equals x. Okay? And so what I want to do is just start taking note of the points that are on them, but I want to look at them in terms of how they look with vectors. Now, if you're not super familiar with it, remember vectors, we can write them. You may have seen them as something like 3i plus 2j or something like that with little hats, or 3x plus 2j, or just plain as a set of ordered pairs. I'm going to mostly write them as a set of ordered pairs, but it just basically tells you go this far in x, this far in y, and basically draw an arrow from where you started to where you ended. So for example, if I look here, if we call the origin our starting position, where the base of our vectors are going to be that are just essentially arrows, we're going to start by looking at the point 1, 1 that is on the graph, and I'm going to draw an arrow out to it. And I can then represent that as the point 1, 1 as an ordered pair, but I'm doing that as the vector 1, 1. And I can look at other points that are on there. I can look at 2, 2. There it is, draw an arrow out to it, and so the vector 2, 2 will also make me land on a point on our line y equals x, and so will 3, 3, and go out to 3, 3, and 4, 4, and so on and so forth. And I can do negative versions of it. I can go back to negative 1, 1, negative 1, negative 1. That vector will keep us on the plane, or not on the plane, on the line. Negative 2, 2, negative 3, 3, so on and so forth. And I even I don't have to just stay at integers like that. I could have 0.5, 0.5, put me right there, 0.5, 0.5. But basically, as long as I keep those two numbers the same, whatever vector I come up with is going to make me land on that line. So what I can do is say, well, as long as those two numbers are the same, and I'm going to write this then as the set of all vectors t, where t can be any number. And as long as it's the same number in that form, then it's going to give me a position on this line. And all these vectors we're drawing then become, that you refer to them as position vectors. And so that's what we'll have right here. And this is basically telling us that all the x values will equal t, and all the y values will equal t for t, I should write this, where t is going to be greater than or equal to negative infinity and less than or equal to, but all the way out to infinity. So basically, t can be anything. And that's always going to put us somewhere on this line, which means I can even represent this line just by telling you this information right here, that x is going to vary according to t, and y is going to vary directly according to t. Now, you're maybe thinking, well, how is that, very helpful? Well, it's usually pretty helpful when you're doing things like trying to figure out the motion of a particle or how something is moving, where you have to look at the two motions independently. If you go to physics, this is actually something you kind of do without really realizing when you're doing projectile motions and things like that, where the x and y directions are actually independent of each other, and they typically have no effect on each other, and you're using this t variable as the time, and you're looking at, as time goes on, it moves this much in the x direction and this much in the y direction. So it's very helpful in situations like that. And so let's take a look at another version. So let's say we have the same slope of line, but this time it's shifted up 3. So that's supposed to look parallel to the other one. So let's say it's this, and this is the line y equals x plus 3. So how are we going to go about doing that one? Over here, this was pretty easy. Well, what we do is we note that, one, we just move this up, and we have the same sort of vectors pointing along it. These t vectors, these same ones, just like this, that can take us both ways. except one key difference is we have this vertical shift here for every one. So as long as we go up this vertical shift and then follow one of these directions, we're always going to land on our line, just like that. Up the 3 and then on the line. Up the 3 and then all our vectors that we had from before, that same set of every possible vector that was TT will be on there. So for the y equals 3 one, right? So for this one, let me put a note here. This was for y equals x. What we're going to do for y equals x plus 3 is we're essentially going to have the same t, but we're going to add on this other vector. This vector here, this blue vector, is the vector 0, 3. It's 0 in the x direction and 3 in the y direction. And we'll get 0, 3, just like that. And so we add those two together, and we'll get t, and then t plus 3. And that's going to be our parameterization in vector form. And so this one tells us that x equals t, and this one here tells us that y equals, let me move that over a little bit, sorry, that y equals t plus 3, and this is again for all t. T's are not bound, they can be anything, negative infinity to positive infinity, and that right there would be our parameterization for y equals x plus 3. Now, you may also want to note that none of these parameterizations are unique. We could have done this in a totally different way. I could have instead used this shifting vector over here to move me off the origin. This is the, this would be, what would this be? This would be just 0, negative 3. And I could have, oh, I'm sorry, that's wrong. This is negative 3, 0. And that could have shifted me over, and then I could have used all my possible t vectors, and I still would have landed on there, and so it would have been something more like, it would have been t minus 3, and then t is what we would have ended up with there, and it would have been a different parameterization where x equaled t minus 3, y equaled t, and again for all t, but it would have given us the same thing. And you should also note that if you do substitution here, you should get back, right? You should get back the same function that we were trying to do, the one that we already knew. So for example, if I look up there, and this is again y equals x plus 3. If I look up here and I say, hey, t is equal to x, that means I could substitute in. I could substitute in for x into t and get y equals x, which is what we were trying to do there. And then over here, I could say, hey, x equals t. I could substitute that in, and I'd get y equals x plus 3. And then over here, I'd say, hey, x equals t minus 3, sorry, which would mean that t equals x plus 3, which means I could substitute that in right there, and I would get back my y equals x plus 3, which is, again, what we were doing. So these two are equivalent, and you don't even have to do something that simple. You could pick some other crazy vector that goes off and touches it anywhere, or do many sorts of things. There's literally an unlimited number of ways to parameterize those. So let's look at another example here. Let's say this time that we have the function, we're going to go with 2x. Y equals 2x. And so here, y equals 2x is going to be a little different because we're not just going to use the regular vector tt to get onto it. What we'll have is if we go out in x, we have to go up 2 in y. So our actual vector that would keep us on that line is not 1, 1, but rather 1, 2. And then another vector that would keep us on there would be 2, 4. And so you should start to notice the pattern here. We could also do -1, -2, right there, and -2, -4, -4, -8, so on and so forth. So as long as we're following that pattern, that the y value is twice that of the x value, we are staying on this curve, which means the family of, or the set of all the vectors of the form t and 2t will actually parameterize that line. And so we get x equals t, and we get y equals 2t. And again, our t can be from negative infinity to positive infinity. I'm not going to write it out again. But this parameterizes it for us right there. And this is for y equals 2x. And again, if you substitute that in, you get right there for t, you substitute in, you substitute in 2x, you substitute in this x for t, you'll get the y equals 2x, which is what the function was we were originally doing. Now, you can do the same sort of thing again that we did above, where this could be shifted around. So maybe say it's shifted down 2 or something like that. And then this would be the function, y equals 2x minus 2. Sorry, I'm kind of running into the other thing over there. But that would be that function, which means we could just simply use a -2 vector, a 0, -2 vector to add on to that. And we would get t plus 2t, because it's that same line with the same slope, plus 0, -2. And that's going to give us t and then 2t minus 2. And now we have a shifted version of this where x equals t, y equals 2t minus 2. And that's our parameterization. Again, t from negative infinity to positive infinity. And again, if you take that and substitute in for t right there, bad line, substitute in for there, you get y equals 2x minus 2, which is what that function is. But you can also have another way to write this function. Again, you could do a different shift, because this function can also be written as y equals 2 times x minus 1, in which case this looks like a slope of 2, same slope, but it's a shift to the right 1. And I didn't draw this very well, my original red line. It should have gone through that point right there. It should have gone through the 1, 0 point right there. In which case, so this is the exact same line as this one. These two are samesies, they're the same. And I could parameterize it that way. Again, like I was doing before, where I could have done, say a horizontal vector, the vector 1, 0, to shift all of my other vectors over and put me onto that line, and let me do something like that. And I could have made it as, it would have been t plus 2t, so our same slope line there, plus this time 1, 0. And if I do it that way, what I do is I end up with over here I get t plus 1 and then 2t. And that's my coordinate. So x is going to equal t plus 1, and y is going to equal 2t. And again, if I try to combine them together, if I substitute in over here, I solve that for t, I get t equals x minus 1, and if I plug that in, I'm going to get y equals 2 times the quantity x minus 1, which would give me, if I distributed, 2x minus 2. So this is, again, for the 2x minus 2. This is the y equals 2x minus 2, and this is the y equals 2x minus 2. They both turn out to be that, which is also 2 times the quantity x minus 1. All right, so that's how this basically works. So what I'm going to do is give you a quick challenge here before I end this video and start the actual notes. And my challenge to you is, before you watch my video on the notes, is I want you to try to parameterize a curve instead of just a straight line. And we'll do something simple, and you should try and parameterize y equals x squared. And if you were able to get that, you'll know if you're successful if you get a good parameterization for it. Notice I said a parameterization for it, not the parameterization for it, because again, there's a lot of different things you can do. See if you can figure out a way to get a parameterization for it. And then try and do some other ones. Try and see if you could do this one where it's, say, shifted down by 3. 1, 2, 3. All right, see if you can do that one. See if you could do one that's then shifted down 3 and maybe flipped over. All right, so this one would be y equals x squared minus 3. This one would be what? Y equals negative x squared. Hold on. Negative x squared. And then I think I want my parentheses on there like that, right? Negative x squared minus 3. So I'm negating the entire thing. I think that's right. Although I do not want my parentheses around that. So plug in. Yeah, I want it like. No, I don't want the parentheses on there. Sorry. Like that. Negative x squared minus 3. All right, so see if you can try those ones, see if you can come up with something successful. And again, you'll know you're right if you plug in, if you substitute one or the other and get back these original equations. But just a little challenge for you, see if you can do it. And the next video will be the actual notes for this. All right, that's it.